Hello, everybody. My name is Olga Golko, and this work was done in collaboration with Theta Chen, Moshe Goldstein, and Guy Cohen. If you'd like to learn more, please check out these two papers. The older paper on the transient dynamical phase diagram of the Spin-Boson model at low temperatures, and then our most recent one specifically at finite temperature. So Andrea already very nicely briefly introduced the model. Let me just summarize what the Spin-Boson model is about. It's a fixed spin, or a two-state system, which is coupled to a bath of non-interacting harmonic modes, or bosons. And it's a paradigmal model to study quantum dissipation, but also, of course, very useful to study interactions with photons or phonons, and even fermionic systems via mapping called bosonization. These are the ingredients of the Hamiltonian. We have the two-state Hamiltonian. Epsilon is the energetic bias, and in my talk I will limit myself to unbiased systems, so epsilon is always 0. Delta is the diabatic coupling that characterizes the tunneling between the two states, and the sigmas are Pauli matrices. Then we have the Hamiltonian of the bosonic bath, which is just a sum of harmonic oscillators, and finally the spin-bath coupling that's assumed to be linear, and the coefficients ck characterize the coupling to the bosonic mode with frequency omega k. Now, in the thermodynamic limit, we can characterize the coupling in terms of a spectral density in this compact form. J of omega is assumed to be smooth, and for frequencies below a certain cutoff, omega c, which characterizes the relaxation timescale of the bath, it's of the form omega to the power of s. In our work, we assume an exponential cutoff, and alpha is the coupling strength. Now, depending on the value of this exponent s, we have very different physical regimes. S equals 1, the ohmic regime, is perhaps the most widely studied, and a lot is known analytically about this regime. S greater than 1, the super-ohmic regime, in this case, tunneling always outweighs the weak coupling, and the system is always delocalized. And what I'm going to be talking about is the sub-ohmic regime that has a very interesting physical and mathematical structure, including a quantum phase transition. This is our initial condition. The bath is assumed to be thermalized by itself, and then the system is held fixed in one of the two states. Now we're interested in dynamics, so we need to perform the diagrammatic expansion in real time, which of course is much harder than an imaginary time expansion. We use the Keldysh formalism, so vertices are inserted on either branch of the Keldysh contour. The observable is at the Keldysh fault, and then we can sort of unwrap the contour and perform updates in a similar way as the typical imaginary time updates. Now, the challenge is how do we design efficient real-time quantum Monte Carlo updates, and one way to achieve that is the Inchworm algorithm developed by Guy Cohen. So in this case, the full propagator is extended in an Inchworm step by just a tiny amount in time. And the idea is that short-term propagators are cheaper to compute than long-term ones, and then this information can be reused in subsequent time steps, which reduces the scaling from exponential to polynomial. The observable we're interested in is the non-equilibrium population difference, so the difference in occupation between the two states, sigma z. Here, this data is kind of in the middle of the sub-ohmic regime at low temperature and high cutoff. Alpha, again, is the coupling strength. We start fixed in one of the two states, and then we evolve in time. And so you can see here the different types of behavior. We have coherent oscillations at low coupling that then become incoherent decay at a larger coupling. Also, at low coupling, the system is delocalized, so it tends to 0 at very long times. But at larger coupling, the system may be localized, so may retain some memory of its initial state. Here's a more detailed plot of the dynamics, so kind of the curves you saw before would be sections like this, and this plot, red and blue, would be the oscillations. I'm showing you data deep in the sub-ohmic regime on the top, closer to the ohmic regime at the bottom, low temperature on the left, and high temperature on the right. And so what you can see here as well, the system becomes localized at larger values of the coupling, and the transition does happen at larger alphas if we are at larger values of s. And we also see the loss of coherence. So we see that oscillations become damped with increasing coupling, but actually we see more than that. We see that there are two distinct mechanisms at play here that govern the loss of coherence. Aside from the damping of the amplitude that we can observe in both panels, we see that there's also a tendency for the frequency to go to 0, but we only see that for S closer to the ohmic regime. And then as temperature is increased, well, the system becomes more delocalized as expected and less coherent, but we also see some non-trivial frequency shift, which I'll discuss a little bit more at the end of my talk. So just very briefly, Andrei mentioned that, how we fit our simulation data. So this is just a heuristic fit, an expression that describes well the data and captures the different physical regimes. We have damped oscillations, just a decay term, and then an offset. And so if the offset is compatible with 0, then we're delocalized. Otherwise, we're localized, and we can study the frequency and the damping of the oscillations and compare the two mechanisms. And so it is known that in equilibrium, there is a quantum phase transition between localization and delocalization, and the details of this transition are known. And so these are our results, which Andrei also showed in part 1 of these curves. So this is the offset C, and you can see here plotted for s smaller equal to 0.5, how there's a sharp increase at some point corresponding to the transition. So this is data extracted from our short and intermediate time simulations. And it looks, in fact, very different from the equilibrium data, which this has been studied by different groups before. So you can see, in particular, that the critical exponents are very different. So in equilibrium, the critical exponents are known. There's a mapping to the classical Ising spin chain with long-range interactions. And in this regime, the exponent is 1/2. It kind of goes like this, but in our case, goes like this. So it looks like the exponent actually must be larger than 1. So what we see is that it is very difficult to reach equilibrium. We need very, very long time scales. So the dynamics that's accessible to us in the simulations and would be maybe accessible in dynamics experiments will show a very, very different picture, this transient dynamical picture, which is quite interesting. So let's talk a little bit about the loss of coherence, here shown at low and at high temperature. And I mentioned the two mechanisms for the loss of coherence. So on the one hand, we have overdamping, here shown as the ratio between the frequency and the first damping term. And this is a very smooth crossover. So we set a threshold at omega equals to gamma 1 to define the overdamping. So kind of for all values of s as expected, we see the smooth decay. Now it looks very different when we look at it in terms of omega. So here, for certain values of s, for large values of s, we see a sudden sharp drop to omega equals 0, which is more reminiscent of a transition than a crossover. We don't see it for smaller s, which also have some non-monotonic behavior. And so these two mechanisms are clearly very different from each other. Now at high temperature, when we look at the damping-driven crossover, it's kind of as expected. It smoothly moves to lower values of the coupling, so the system is less coherent. But it's quite different picture when it comes to the omega transition. So first of all, now we see the sharp drop for all values of s. We also see a very sharp increase at small alphas that precedes this drop. And again, we see that all of these critical values move to lower coupling. So to summarize my results, we can draw a phase diagram at low temperature and at high temperature. This shaded region here is our error band, our confidence interval for alpha star, which is the transient dynamical localization transition. And it agrees quite well with the equilibrium transition coupling at small values of s, but not at larger values of s. And we see also the two lines here for the two mechanisms of the loss of coherence. As we increase temperature, so the system becomes more delocalized, so this region moves down, but the error bar that we have is actually quite large, so it's a little bit hard to tell. These two lines as well move down, so the system becomes more incoherent. And what's quite interesting is the interplay between them, so the relative location. Here, the incoherence lines are above mostly the localization line, but then they move below at the localization line. So with temperature, this picture changes. So this is all that I have to say. If you're interested in more detail, I refer you to our papers, and I'll be happy to answer questions.